All right. Sometimes when we're modeling data, a lot of times actually, it starts to grow exponential at first, but then it slows down as it approaches some highest value. And that highest value is called the carrying capacity. And that's really, if you think about this in like a biological sense, it's how much that like a certain area can sustain. So maybe you're modeling a herd of elk. There's only so many elk that a certain area can contain for grass and space and all the things that the elk need. So we call that the carrying capacity. And when we want to use a model that has exponential growth up to a point, but then slows down approaching a specific value, that's called a logistic growth model. So here we are in 6.7, we're on video number 2, and we're going to talk about logistic growth models. So this is what I was sort of talking about. Here's a nice graph of it. You can see it's growing exponentially through here, but then as time goes on, it approaches this carrying capacity, and that's the largest amount that it can possibly reach. Here is the form for logistic growth. And this one's a little bit harder to solve for, but we will be working with it quite a bit. So let's give this some work with. One important point to notice is the initial value of the population is given by 0 c over 1 plus a, because again that e to the 0 becomes a 1. The point of maximum growth occurs at the natural log of a over b, and the output there is going to be c over 2. And the carrying capacity is the c value, is that whatever that is given in the numerator of the logistic growth model. All right, so we just had a few things to point out. Let's go ahead and practice using this model. Let's talk about spread of the flu. Seems timely, right? A flu epidemic spreads through a population rapidly at a rate that depends on 2 factors. The more people who have the flu, the more rapidly it spreads. And the more uninfected people there are, the more rapidly it spreads. Here is a logistic growth model, IFT, that gives the number of people in a town who become ill with the strain of influenza T weeks after its initial outbreak. How many people will become ill with the flu when the epidemic began? So what we're asking is, what is the initial value? So we're going to find, we could go up and just use this that we figured out here, c over 1 plus a, but let's just go ahead and plug it in. It's easier for me to just go, I want to find I of 0. Well, I of 0 is going to be 30,000 divided by 1 plus 20 e to the 0. Negative 1.5 times 0 is 0, right? So this is 30,000 over 1 plus 20, which is 21. And if we take 30,000, and we divide it by 21, we get 1428.57. Since we're talking about people, we need to round to 1,429 people became ill with the flu when the epidemic began. How many people were ill with the flu by the 4th week? Well, T is given in weeks, T weeks after the initial outbreak. So if we're talking about the 4th week, we're going to set T equal to 4. So we're going to find I of 4. That's going to be 30,000. 1 plus 20 e to the negative 1.5 times 4. All right, so we're going to use our calculators to come up with some values here. So let's take 1 plus 20 e to the negative 1.5 times 4. And I get 30,000 divided by 1.0496. I'm not going to round in my calculator. I'm just going to take 30,000 and divide it by the previous value. And that gives me about 28,582.9, so about 583 people in the 4th week. What is the limiting size of the population that becomes ill? Well, remember when we talked about logistic growth, that numerator value is your carrying capacity. So in this case, our carrying capacity is 30,000. That's probably the population of the town. So 30,000 is our carrying capacity. So that's the limiting size. All right, for some reason I have a D problem in here that I don't want. So let's just skip over and go to the real D that I actually want to do. In which week does a flu have its maximal growth? Well, if we remember when we first discussed logistic equations on the previous page, it told us where our point of maximum growth would occur, and that's at the value of natural log of A over B. So for this case, our A is equal to 20 and our B is 1.5. So we need to calculate the natural log of 20 divided by 1.5, and that will give us the time, the week, for our maximum growth. So we'll take natural log of 20 and divide that by 1.5, and we get 1.997. So this is week 2. All right, if we wanted to find that maximal growth, we could plug 2 into our equation I of t. If we plug in 2, we get, let's quickly do this. I got 15,032 people. That was the maximum, the amount at a time of maximum growth, the amount of people with the flu at the time of maximum growth. So let's just go over some of the models we have now and make sure that we know which model to use based on the shape of our data. So the first one here you can see is exponential growth, and it's going to look like this. It has that horizontal asymptote at 0, and it's going to increase. The second one is exponential decay. So if your data looks like this, you should use exponential decay. Here, it logarithmic grows with A and B both greater than or equal to 0. If your data looks like that, you should use logarithmic growth. And here is logarithmic decay. You're going to have B less than 0 on this one. And again, we always have positive linear and negative linear as well. All right, so let's go ahead and try an example of modeling some data with one of these possible scenarios. So we're going to use Desmos to help us because Desmos is a great tool for doing exponential regression. So what we're going to do is we have some data. We did some research to see how grass would grow near a certain lake. We planted some grass seed in the ground near the lake, and for the next 9 days we came back each day to see how much it would grow, and we measured it. Here's the data that we collected. We're going to plot the data in Desmos. We're going to look and see which we think is the most appropriate model, the choices being linear, exponential, or logarithmic. So we're going to decide which is the best fit. We're going to decide how well that model fits the data. We're going to use that data to predict how tall the grass would be in 2 weeks, so that would be day 14. And we're going to decide if this is extrapolation or interpolation for the answer to number 5. So let's pause this video now. I'm going to head over to Desmos and we're going to put this data in. All right, here we are in Desmos and we're going to try and model this data. Let's go ahead and plug it in. All right, so I'm going to make a table. Where's my cursor? There it is. I'm going to go here. I'm going to make a table. And I'll call this T for time and H for height of the grass. And let's put the data in. We have 0, 0, which I'm actually going to, go ahead, put it in 0, 0. We might skip that one later. I'll tell you why. 1, 0, 2, 1.386, 3, 2.197, 4, 2.773, 5, 3.219, 6, 3.584, 7, 3.892, 8, 4.159, and 9, 4.394. All right, there's our data, and we're going to decide which model is best. We're going to choose between linear, exponential, and logarithmic. So let's go ahead and do our linear model first. H equals mx plus b. Oh, not xt. H equals mt plus b. Yeah, it's actually not a terrible model for it, is it? And let's do exponential. H is a times b to the t. All right, that one's actually not quite as good, is it? No, not quite as good. And finally, let's do our natural log model. Now, I know right off the bat that my natural log model is going to have a little bit of a problem because of this first initial value, the 0, 0, because I can't take natural log as 0, okay? So the way I'm going to do that is I can do two things. I can either delete this data point, or instead of using H equals a plus b natural log of x, I could do a shift, okay? So I actually used a in the notes, so let's change that to a, that's fine. Oh no, what have I done? I've just messed the whole thing up. Twiddle, a, there we go. Let's do a plus b natural log, and it's not going to like it if I do natural log of t. I can tell you right now, see, it's not going to do anything because it won't take the natural log of t. So let's just add a shift in, so we'll just put a plus or a minus c into the right, t minus c. Let's put another parameter to shift that graph, just so we don't have to worry about that 0, 0 value. So it's shifted just a little bit. We're good at shifting. We've been doing this all term. All right, so here's our 3 models. Wish 2 weren't green. Let's make this one purple, shall we? There we go. All right, so there's our natural log in purple. Our linear is in green, and our exponential is in blue. Which one is the best model? Well, let's look at our R-squared values. This has 0.9356, this has 0.8035, and this has 0.9738. So I think this is actually our best model. It has the highest R-squared value. So that's the model that we're going to use. All right, so what were the questions we had to ask? We had to plot the data in Desmos. We did that. We matched it with the most appropriate model. And which is the curve of best fit? We decided the natural log was the curve of best fit. Suppose it was decided that they will introduce this grass to the lake. Use the model to predict how tall the grass will be in 2 weeks after introduction. So what we need to do is I'm going to actually just make this into a function I'm going to write down below. So we're going to use h of t, and I'll just use capital H so we don't get confused. H of t equals, my a value is negative 5.24627 plus my b value is, just reading it off Desmos, 3.87067 natural log of t minus my c value, which is minus, so minus negative, so we'll just make that plus, 3.5755. So all I did was I looked at my A, B, and C parameter values right here, and I plugged it in, and something it does not like. Oh no, what have I done? Well, we should do that again. Let's try that again. Maybe it doesn't like h of t. I don't know. Equals a. I wonder if I can copy and paste to make my life a lot easier. No, I can't. Negative 5.24627 plus b 3.87067 times the natural log of t minus negative 3.5755. Why is it not liking this, I wonder? Oh, it doesn't like me to use t. Let's just use x, fine. There we go. All right, so this nice black one is just this model purple one, overrun. So let's turn these guys off because we decided we didn't want to use them. And this is the model that we're going to use. And now to make our prediction, what's it going to be like in 2 weeks? Well, that's 14 days. We can find h of 14. Oops, I could use parentheses, that would help. H of 14, Desmos tells me, is 5.849. So we would approximate that the grass would be 5.849 inches tall. And do we think this is extrapolation or interpolation? Well, it's after our data period, right? Our data goes between 0 and 9 days. This is at 14, so it is going to be extrapolation since it's not between the interval. So that's how you do all those types of regression on Desmos and how you choose the one that you think is the best fit.